The Geological History of Iowa, prepared by the Iowa Geological and Water Survey with assistance from the Iowa Limestone Producers Association. Part 7, the Cenozoic Era, from 65 million years ago. The Cenozoic Era is the last of the three eras that comprise the Phanerozoic. It includes a period of 65 million years, between 65 million years ago and today. The Cenozoic is divided into three periods, the oldest, Paleogene, between 65 and 23.3 million years ago, the middle Neogene, from 23.3 to 2.588 million years ago, and the youngest Quaternary, from 2.588 million years ago until today. In the past, Paleogene and Neogene were combined and called the Tertiary. Today the term tertiary is still frequently used, but officially it has been discontinued. As we get closer to the present, accurate age dates become more precise, and geologic record is more complete, allowing a finer subdivision. So, periods are subdivided into epochs, as shown in this chart. Some of the major events in Cenozoic history include the beginning of the evolutionary radiation of mammals into many ecologic niches following the Cretaceous-Tertiary extinction event about 65 million years ago, and the appearance of Eohippus, the first horse, 55 million years ago. The first camels, Protolupius, appeared 40 to 45 million years ago, and the first proboscideans, or elephants, about 35 million years ago. Cats and dogs evolved at about the same time, 25 million years ago, and the first bovids, cloven hoof animals such as cattle, sheep, and goats, appeared about 20 million years ago. Most recent episode of continental glaciation on Earth began about 2.6 million years ago, with about a dozen ice sheets sweeping into Iowa, the last of them departing the state only 12,500 years ago. The first modern humans diverged from their last common ancestor about 2.4 million years ago, and finally the last of the continental ice sheets melted from North America about 11,700 years ago, marking the beginning of the modern age, the Holocene. Only the Pliocene and the Pleistocene have sediments that are known to be preserved. By the Paleogene, the continents were approaching their current configuration. The Earth, cooled by the effects of the Chicxulub meteor impact that marked the end of the Cretaceous, had slowly warmed, melting the polar glaciers and reaching its peak temperature about 55 million years ago, when tropical climates were present over most of the globe. By the end of the Paleogene, the Earth's atmospheric temperature had cooled to near modern values, and the polar ice caps had returned. During the Paleogene, the oceans mostly regressed to their basins, and the major rock deposition in North America was occurring in a series of large lake basins in the western U.S. Iowa, marked by the red asterisk, was distant from these depositional environments, and no Paleogene rocks are known from Iowa. The Pliocene landscape was populated by many familiar-looking animals, as well as some that have no living relatives. In these dioramas we see A, an early primate, B, Oreohippus, an early rhinoceros, C, Tragulus, or the mouse deer, an extinct genus of forest-dwelling mammal, D, Hyracotherium, or Eohippus, an early horse about the size of a small dog. E is another primate. F is an oreodont, or a ruminating hog, an extinct hog-like animal that is actually related to the modern camel. G, Hyracodont's, or the running rhinoceros, an extinct deer-like rhino. H, Oreohippus, or the mountain horse, is a small four-toed horse. I, Mesohippus, the three-toed horse, a small horse about the size of a deer. J, Hoplophonius, the saber-toothed cat about the size of a leopard. And K, Archaeotherium, a cow-sized relative of today's pig. I can't believe it. The Neogene period from 23.3 to 2.588 million years ago is sometimes called the Age of Hominids, since that was a time when the ancestors of man emerged. The distribution of the continents and the seas on Earth looks similar to today with a number of minor differences. Sea level was still higher than today, with water covering most of Florida. A seaway was still partially open between North and South America, and much of Eastern Europe was still submerged. However, the ice caps were forming on the North and South poles, and they were drawing water from the oceans. Iowa, located by the red asterisk, was landlocked, so there are only a few Neogene sediments in the state's geologic record, materials eroded from the rising Rocky Mountains. But geologists can look at rocks in nearby areas to gain an understanding of what was happening in Iowa at that time. An ever-increasing variety of animals roamed the Neogene landscape. One of the animal groups that evolved rapidly in the Neogene were a group of primates known as hominids, or great apes, the ancestors of modern humans, leading many scientists to refer to the Neogene as the Age of Hominids. These paintings illustrate some of the animals of the Neogene. A is Amphicyonidae, a bear dog, an extinct family of carnivores. B, Menoceras, an extinct genus of small rhinoceros. C are early camels. D, Amyobelodon, a shovel-tusked mastodon. E, Paleocastor, a prehistoric beaver. F, Mesohippus, the three-toed. G, Chalicotherius, the extinct relatives of modern horses. H, Tomarctus, early dogs. I, Oreodont, or ruminating hogs, extinct hog-like animals related to modern camels. J, early. K, Poebrotherium, the early camel. L, Teleosaurus, Eocene rhinoceros. M, Entelodont, the giant pig. And N, primates, the ancestors of modern humans. Another interesting animal that reached its peak during the Paleogene were the phorusrhynchids, or terror birds, like Diadema, shown here, about to eat an early horse. These flightless carnivorous birds stood 3 to 10 feet tall and evolved in South America, but migrated northward, and their fossils have been found in the southern U.S. The only Neogene units that are known in Iowa are the sands and silts collectively known as the Salt and Pepper Sands. They were deposited as sediment shed off the uplifting Rocky Mountains and are an eastward extension of the Ogallala Formation of Nebraska and the adjacent states. As this map shows, they cover parts of the western half of the state and were deposited by a series of rivers that flowed eastward, eventually joining the Mississippi River. Numerous Neogene fossils have been found in Iowa to confirm the age of this unit, most notably a snail found by drilling in Cedar Rapids. Salt and pepper sands have also been found in several wells in the Gordon Channel, a deep river valley incised into bedrock in Lee County. This confirms that this channel was used to carry water from the west at that time. The only exposure of salt and pepper sands is in the Folsom Quarry in Mills County, shown by the red star. These sands and associated sills have not yet been consolidated into rock. Salt and pepper sand was originally a term used by well drillers to describe the white and black speckled colored sand. As can be seen in this photomicrograph, the salt is quartz sand and the pepper a volcanic glass that came from the west. By the Quaternary, about 2.6 million years ago, the configuration of the continents was very similar to today. Known as the Age of Glaciers, the Quaternary featured some of the most extensive continental ice sheets in the Phanerozoic. These ice sheets periodically grew to the size of continents, covering as much as a third of the Earth's land surface, with ice up to 2 miles thick. At other times they retreated, ushering in interglacial periods of warmer temperatures and the proliferation of plants and animals. The Quaternary period is subdivided into a lower Pleistocene epoch, which represents about 99.5% of the Quaternary, and the Holocene epoch, the last 11,700 years of the Earth's history, and the uppermost 0.5% of Quaternary history, sometimes called the Age of Man. Because the Quaternary is the most recent period in the Earth's history, it is best understood, and we will investigate the Pleistocene and the Holocene epochs individually. The animals of the Pleistocene include some which are very similar to animals living today, some which are similar but much larger, and some that are similar but have peculiar adaptations that are no longer seen today. A is dire wolves, the relatives of today's wolves but larger. B, horses. C, a ground sloth, a giant relative of the smaller tree sloths that live today. D is mammoths. E, bison. F, large saber-toothed cat. G, early horses. H, woolly mammoths. I, cave lions eating a reindeer. And J, woolly rhinoceros. Probably the most dominant feature of the Pleistocene were the widespread continental glaciations that buried up to 1/3 of the Earth's land with ice. These glacial advances mostly affected the northern hemisphere, blanketing most of North America and Europe and much of Asia. Snow accumulated in 2 areas of Canada in depth sufficient to compress and form ice, which flowed outward from these spreading centers, eventually moving into the United States and Iowa. Geologists' understanding of the sequence of periods of glaciation, times when glaciers were advancing and retreating, and interglacials, the warmer periods between the glacial advances, has evolved through the years. The order of events in the terminology shown here was generally accepted for many years and is still being used by many geologists. It was believed that there were 4 glacial stages, or periods of ice advance, with intervening interglacial stages. However, with research conducted principally in Iowa, it was determined that the period represented by the Kansan and Nebraskan glacial stages actually included many more separate ice advances, and that the first ice advance was much older than 1.8 million years ago. So most geologists have discarded the terms Kansan and Nebraskan, as well as the intervening Aftonian interglacial, and they have combined all 7 of these early glacial and interglacial stages under the name Pre-Illinoian. We know that there were as many as 7 individual glacial advances and associated interglacial periods in the Pre-Illinoian of Iowa, but they are very difficult to differentiate. Geologists are working to understand these Pre-Illinoian glaciers and will eventually assign a name to each. Note that this chart does not show the intervals of time with a uniform time scale. If we expand the chart to a uniform time scale, you see that the Pre-Illinoian constitutes the largest period of the Pleistocene. The term Ice Age is generally used to refer to the period of time when glacial ice was making large-scale advances and retreats, beginning about 2.588 million years ago and continuing to about 11,700 years ago. So if we look at the ice stages, as indicated by the blue bars, does it look like the Ice Age is over? Most geologists agree that it's not, that the Holocene is just another interglacial period, and the glaciers will be coming again. Human activity that is warming our planet today probably slowed down the return of the glacial conditions, but they will. Let's look a little closer at the Pleistocene glaciation in the area around Iowa. The Pre-Illinoian ice sheets advanced at least 7 times into Iowa between about 2.6 million and 500,000 years ago, completely covering the state. The maximum glacial advance was to about the center of Missouri and the southern part of Illinois. The ice then retreated to the north, ushering in the Yarmouth interglacial period. About 300,000 years ago, the ice advanced again, this time from the east, the Labrador spreading center. It moved south across Michigan, Wisconsin, and Illinois, and into the southeastmost part of Iowa. After several retreats and readvances, the Illinois ice finally retreated to the north, and the Sangamon interglacial period began. The last of the major glaciations was the Wisconsinan, often referred to as a Laurentide. This advanced only into eastern Illinois and to north-central part of Iowa, with several ice advances and retreats into each state. It's interesting to note the area of southeastern Wisconsin and adjacent Illinois that was bypassed by all of the glacial ice. This area is referred to as the driftless area because it contains no glacial deposits that are sometimes referred to as glacial drift. An area of northeast Iowa where most of the glacial sediments have been eroded away is often considered part of the driftless area, but scattered remnants of glacial materials indicates that Iowa in total was covered by glacial ice. Glacial materials and processes have been the principal agents in creating the landscape of Iowa. They are the geological materials that we interact with most frequently, and they are very important to the economy of the state. This is quite evident in the aerial photograph of Winnebago County in north-central Iowa from the spring of 2004. The rich, flat soil makes this area ideal for row crop farming, as is evident from the amount of land that has been cultivated. The soil is very fertile because it was produced by glacial grinding of mineral-rich rocks, producing roughly equal proportions of sand, silt, and clay. The land is flat because the glacial ice only departed about 12,000 years ago, and the landscape has not had sufficient time to develop a river drainage system. This is both a blessing and a curse, as this photo shows. During the wet spring, the water pools on the surface, and the natural drainage isn't present to remove it. The water accumulates in low depressions known as kettles, inhibiting farming activity. In the following section, we'll learn more about glacial materials and features, such as the kettles. There are three principal categories of glacially dry sediments in Iowa: glacial till, outwash, and loess. Glacial till is a product of glacial ice plucking, grinding, and incorporating materials from all of the bedrock that it passes over. A variety of processes combine to create this material, which in Iowa is composed of almost equal portions of clay, silt, and sand-sized particles, with pebbles, cobbles, and boulders added into the mix. Iowa till has a greater concentration of clay than most tills because of the Paleozoic and Mesozoic shale units that the glacier passed over. This clay content is one of the factors making Iowa's soil so productive. Outwash includes material that is carried from the glacier by water produced by the melting ice. Although outwash usually refers to sand and gravels deposited in moraines and outwash channels, it also includes a variety of other products, from sands and silts and clays that were deposited in glacial lakes. Loess is windblown silt, a fine sand that was originally deposited in the floodplains of the river that were carrying the glacial meltwater, then later blown up into the landscape by winds. Iowa has multiple generations of loess, produced by each advancing and retreating ice sheet. One other glacial term that I'd like to discuss here is erratics. Erratics are rocks that were not derived from the local bedrock, but were carried into the area by glacial ice. Erratics are technically just a component of glacial till, but they deserve mentioning because they can be such a dramatic feature. As mentioned earlier, glacial till is composed of a variety of materials produced and deposited by a variety of processes, many of which are on display on this illustration of a retreating ice sheet. Superglacial materials are materials on top of the glacial ice and include sand, gravel, silt, and clay deposited by rivers running on top of the ice. Melt-out sediments that are a lag deposit of the materials that were in the ice but were left behind on the surface as the ice melted. Sand, silt, and clay can be deposited in lakes that form on the glacier. Material within the ice, everything from clay to boulders, settles down on the ground when the ice melts. This is called a melt-out till. Subglacial materials are materials beneath the glacial ice. These include sand, gravel, silt, and clay deposited in rivers that were running in or beneath the ice, and basal till, including materials that melt out of the glacier's base. But when the ice has finally departed, all of the material left behind is called glacial till. Moraines are linear ridges composed dominantly of sand and gravel that form on the edges of stagnant glaciers. They create a landscape called knob and kettle topography and are most evident in north-central Iowa. In this illustration of a slowly advancing glacier, the glacial ice is slowly flowing in the direction of the dark blue arrow. But since the ice is a liquid, a very viscous liquid, it's also flowing toward the flanks of the ice sheet in the direction of the light blue arrows. However, the ice movement to the sides is equaled by its melting, so the ice sheet appears to be unmoving or stagnant in those directions. As the ice flows to the margin of the ice sheet, it carries with it sand, gravel, rocks, and other materials which pile up on the edge as the ice melts, forming the moraines. Here's another illustration of a moraine being constructed when glacial ice is stagnant. Stagnant does not mean the ice is not moving. It's always flowing toward the edges of an ice sheet in the direction of a gray arrow. However, if the outward movement of the ice is equaled by its melting, the ice sheet appears to be unmoving or stagnant. As the ice flows to the margins of the sheet, it carries sand, gravel, rocks, and other material which piles up as the ice melts, forming the moraines. See the blue arrow? By following an erratic, the red arrow, we can see how this and other material is carried to the edge of the ice by a glacier, then dumped, very much like a conveyor belt moving material. If the ice melting is accelerated, see the last frame, the material in the ice settles directly to the ground, forming a till plane. This illustration shows a retreating glacier. In other words, the ice is melting backwards, faster than it is flowing forwards, indicated by the gray arrow. You can see the rate of melting by the location of the erratic, pointed out by the blue arrow, and the yellow dashed line that are right at the nose of the glacier in the first frame. The location of the nose of the glacier is identified by a yellow arrow, and the distance between the yellow arrow and the yellow dashed line in the other frames shows you how far it has retreated from its location in the first frame. So by following the movement of the yellow arrow, you can see how fast the glacier is melting back. You can see the rate that the glacier is flowing forward by following a single erratic, indicated by the red arrow. The erratics and other glacial materials that are left behind as the glacier melts away is glacial till. This illustrates a relationship between a mountain glacier and its moraines. Mountain glaciers are thinner and much smaller than continental glaciers, but many of the processes are similar. At its maximum advance, the glacier was stagnant just before it began to retreat. At this point, the terminal moraine was creating, marking the line of maximum advance. The terminal moraine usually corresponds with the maximum width of the glacier in the production of lateral moraines. If a glacier pauses during its retreat, another set of moraines will be produced. The end moraine of this pause is called a recessional moraine, but any moraines that form at the side at this time are still called lateral moraines. Retreating glaciers usually produce many recessional moraines and lateral moraines. This is a shaded relief map of Iowa and the surrounding regions. The hills and valleys have been accentuated by shading. This area in the center identifies the most recent ice advance into Iowa, called the Des Moines Lobe. This ridge on the south end of the lobe is the terminal moraine. These arc-shaped ridges are recessional moraines, formed during times of glacial stagnation during retreat. And these linear ridges are marginal moraines, formed at various ice stages. Moraines from the most recent ice advance, the Wisconsin, shown in dark green, are a very common landscape feature throughout the Midwest. Some moraines from the older Illinoisan ice advance, although less pronounced, may still be visible. See the light green. But moraines from the oldest pre-Illinoisan glacial advances have been obliterated or obscured by erosion and burial by more recent materials. Moraines are frequently sources of valuable sand and gravel deposits that can be quarried for aggregate or other uses. These deposits are generally referred to as upland sand and gravel deposits, since they are not associated with modern river valleys. There are a few other glacial features that are common to rare in Iowa. If we look at this illustration of a glacier again, sometimes river running on top of the glacial ice will encounter a fracture and drain into the ice. These holes that swallow running water are called moulins. Here's a photo of a moulin on an Alaskan glacier swallowing a stream. These glacial streams are usually carrying sand and gravel and other sediments, so as the sediments fall into the glacier, they pile up on the bottom of the moulin, forming a mound of sand and gravel called a kame. There are several large kames in Iowa, including the Ocheyedan Mound in Osceola County, shown here. Rivers that run in ice-walled channels on or within the glacial ice, like the one shown here carrying water away from a moulin, deposit sand and gravel and other materials just like rivers on the land surface. These glacial river deposits form ridges on the land surface called eskers when the ice melts. Eskers are relatively rare in Iowa, but more common in other Midwest locations, such as North Dakota, where they often provide sand and gravel to the aggregate industry. When blocks of ice are separated from glaciers and buried into moraines, they can melt to form depressions called kettles or potholes. These kettles can be large features, such as this one at Frieda Hefner Kettlehole State Preserve in Dickinson County, or smaller ones, such as the water-filled potholes in Winnebago County that we saw earlier. This illustration shows a few other features found in glaciated areas. Glacial streams carry meltwater and outwash sediments away from the glacial ice. Sometimes this meltwater forms an ice marginal lake along the edge of a glacier. When the ice is gone, outwash plains and glacial lake materials and shorelines remain. These can be seen in Iowa as kettles, terminal moraines, recessional moraines, eskers, and ground moraine material. The loess, which is wind-blown fine sand and silt that covers much of the Iowa landscape, is another product of the great glacial ice sheets. These loess deposits are especially thick on the banks of the rivers that carried large quantities of glacial meltwater, such as the Missouri, Des Moines, Cedar, and Iowa rivers. The Loess Hills area, east of the Missouri River, is one of the largest loess deposits on Earth. This loess mantles the glacial materials over much of Iowa. The loess was originally created by the action of the glaciers, grinding the rocks that they picked up into fine sand and silt consistencies. This powdered rock, sometimes called rock flour, was incorporated into the ice, then ultimately melted and moved away from the glacier by the meltwater streams. In the spring and summer, when the glacial melting was at its maximum, the meltwater streams flooded, depositing the ground rock as fine sand and silt or glacial outwash onto the floodplains. Then, when the region cooled and melting diminished, the flooding ceased and the fine sand and silt was blown out of the floodplains and into the uplands. After many cycles of flooding and wind-blown silt, the loess began to build up to great depths and was carried over large areas of Iowa and the surrounding states. Ultimately, the entire state was covered by loess. The only region of Iowa today where loess does not now cover the landscape is the Des Moines Lobe area in north-central part of Iowa, which was recently buried by a new layer of glacial till. One of the most unusual characteristics of loess is its ability to stand in vertical walled excavations. Here's a road cut along Interstate 680 just east of the Missouri River floodplain, where a series of vertical cuts expose over 170 feet of loess, including about 25 feet of Loveland Formation loess deposited between about 180 and 130,000 years ago, about 12 feet of Pisgah Formation loess deposited between about 53 and 25,000 years ago, and 135 feet of Peoria Formation loess deposited from about 25,000 to 12,000 years ago. Another process that altered Iowa's landscape during the Pleistocene primarily affected the northern half of the state. The period between about 21,000 and 16,500 years ago, just after the earliest Wisconsin ice advance into Iowa, was one of the coldest periods of the Pleistocene. Permafrost conditions affected the northern half of Iowa and limited that region to only tundra vegetation instead of the boreal forest vegetation that covered the region. Although permafrost conditions imply that the ground is frozen year-round, when this condition occurs in the more southern latitudes, such as Iowa, the summer heat melts the upper few feet of the frozen ground, a zone called the active layer because of its slushy texture. Under these conditions, with no deep tree roots to anchor the upper layer of the soil, the process of solifluction can operate. Solifluction is a gravity-driven downslope flow of materials in this melted active zone. This flow has been observed in Alaska on slopes as low as 5 degrees. The solifluction process worked to level the area of the permafrost by moving the materials from the high areas and filling up the low spots. This cartoon of a cross-section through the landscape shows how the solifluction erosion affected northern Iowa. At the beginning of this period, the landscape of much of Iowa looked like this. Deposits of windblown loess lay on top of a thick ancient soil, a paleosol, and a zone of oxidized till that developed on the pre-Illinoian glacial landscape over about 300,000 years. The solifluction process eroded and leveled this landscape, eventually removing all of the loess, the paleosol, and the oxidized layer of the underlying till. Larger rocks that were too big to be moved by the solifluction process were concentrated on the land surface, called a lag deposit or a stone line by geologists. In a few limited areas, for reasons not well understood, this erosion did not occur, and the original landscape was preserved as a series of west-northwest trending linear ridges called pahas, here shown in cross-section. Finally, a thin layer of wind-blown loess blanketed the region. The area of the Iowa surface erosion covered much of northern Iowa, but the region was subsequently altered by other Pleistocene processes. Most of the glacial till was totally eroded in northeast Iowa landscape, exposing large areas of bedrock in the region, now called the Paleozoic Plateau. In north-central Iowa, the advance and retreat of the Des Moines Lobe Glacier into Iowa buried the central portion of the Iowa surface with a new layer of glacial till. And in the northwest Iowa, loess deposits generated by that Des Moines Lobe advance blanketed the Iowan surface in that region with a thick cap of loess. So this is what the landscape in the area of the Iowan surface looks like today. Fairly flat with gently rolling hills. In most areas of the Iowan surface, the action of frost slowly moves rocks in the buried stone line to the land surface, where farmers are forced to remove them in order to till their fields. Some of the rocks in the stone line in the Iowan surface can be very, very large. These large erratics are a common sight in that area, but they can also be found in other areas of the state. This granite boulder looks quite anomalous, sitting alone in this Jones County cornfield. Some of the largest of Iowa's glacial erratics can be seen just east of Allison in Butler County and in the City Park in Norris Springs in Floyd County. But the largest of all known erratics in Iowa can be found a few miles west of Nashua in Floyd County. This is what the rock looked like in the early 1900s when it sat alone on the prairie. This rock measures about 50 feet in length, rises about 11.5 feet above the ground. It is not known how much of the boulder lies buried below the surface. Here's a closer look at a more recent photo of the Nashua erratic. Like the vast majority of Iowa's large erratics, this rock is granite and apparently originated in the St. Cloud, Minnesota area. Here's a 1-minute review of the Quaternary geologic history of Iowa. Between about 2.6 and 0.5 million years ago, during the pre-Illinoian, a series of at least 7 and probably more ice sheets moved into and through Iowa, depositing glacial till and loess. After the last of the pre-Illinoian glaciers had melted away, a period of soil development called the Yarmouth was interrupted in southeast Iowa by the advance of the Illinoian glacier about 300,000 years ago. The melting of the Illinois glacier brought with it another period of soil development called the Sangamon that ended in north-central Iowa by the advance of the first of the Wisconsin ice sheets, the Tazewell Glacier, about 30,000 years ago. With the retreat of the Tazewell Glacier, frigid conditions brought in the development of tundra and the formation of the Iowan surface between about 21,000 and 16,500 years ago. The Wisconsin ice returned to Iowa as the Des Moines Lobe, entering the state about 15,000 years ago and reaching its maximum extent near the town of Des Moines about 15,500 years ago. Finally, as the last of the glacial ice sheets retreated, our map of the Quaternary geology of Iowa was complete, and it is these features that we see at the land surface in most places of Iowa. This is reflected in the landforms map of Iowa, where most of the features are of Quaternary origin. So, we have seen how the geologic history of Iowa can be seen in the rocks, as old as Archean, almost 3 billion years old in northwest Iowa, and continued with the formation and deposition of a variety of Proterozoic rocks, the last of these about 900 million years ago. These oldest rocks are almost entirely buried by the Phanerozoic sedimentary rocks deposited in the numerous seas that transgressed into Iowa in the Paleozoic and Mesozoic eras between about 500 million and 65 million years ago, or in some cases the sediments of rivers that flowed into those seas. Finally, a series of a dozen or so continental ice sheets moved into Iowa over the last 2.6 million years, building and sculpting the landscape. Creating the 7 landscape regions that we call Iowa today. The Holocene includes a period of geologic time from the end of the Pleistocene, around 12,000 to 11,500 carbon-14 years ago, to the present. It has been identified with the warm period known as MIS1 and is considered the interglacial period following the Wisconsin and glacial stage of the current ice age. It includes the development of the human species and their impact on the Earth, including all written history and overall significant transition toward the urban living of the present. The impact of the human species on the Earth and its ecosystems during the modern era are of global significance, and they will and have had effect on the future evolutionary trend of many living species. This has led to the proposal of a new term, Anthropocene, to be applied only to the very last part of geologic time, the period since the Industrial Revolution beginning about 1760 AD. Some geologists have proposed a new time period called the Anthropocene. From the Greek word anthropo, or human, it literally means the age of humans. Not for the evolution of humans, but for the time when humans started to adversely affect the Earth's environment, beginning with the age of industrialization, about 1760 AD. The Anthropocene epoch has not yet been accepted by the geologic nomenclature committees, but a rapid escalation of pollution and negative effects of human-induced global climate change may be an age deserving its own name. It will certainly be associated with another of the great extinction events, as we are currently losing species at a greatly elevated and ever-increasing. The activities of humans have had a greater impact on Iowa than any other state. The major impacts have been the effects of modern agriculture on the landscape. Iowa was originally blanketed by dense native prairies over most of the state, with abundant wetlands in the north-central regions. Most of the wetlands have been drained and the prairies have been plowed. In most areas, like Winnebago County, shown in the aerial photograph on the upper right, it's difficult to find land that hasn't been plowed. In other areas, large cities like Des Moines, the lower right, have developed, replacing the prairies and forests. What does the future hold for Iowa and the world? By studying the past and current movements of the crustal plates, geologists are able to predict where they will go in the future. 50 million years from now, the Atlantic Ocean will have reached its maximum width and will begin to subduct beneath North and South America. This will mean earthquakes and volcanoes up and down the western Atlantic Ocean. Africa and Arabia will have moved northward, closing the Mediterranean Sea and smashing into Europe and adjacent parts of Asia, pushing up the Mediterranean mountains, which will link with the Himalayas to form a nearly continuous mountain chain that runs the length of Eurasia. North America will rotate west, and South America and Antarctica will move north, melting much of the Antarctic ice cap. The Arctic Ocean will slip southward, moving Iceland to the North Pole. Australia will drift north, crashing into many of the islands of the East Indies, including New Guinea. The Iowa area of North America has moved slightly north and will have a climate similar to southern Canada. 150 million years from now, the Atlantic Ocean is still rapidly closing as volcanoes and earthquakes continue up and down the western Atlantic coast. The combined continents of Europe, Asia, and Africa will continue to rotate clockwise, moving England into the Arctic Circle. Antarctica will drift north, crashing into Australia and the southern East Indies islands. They will be drifting toward South America and Africa as the Indo-Atlantic Ocean closes. The Iowa area of North America is beginning to drift south and is now at a latitude similar to today. 250 million years from now, the continents of Earth will be almost unrecognizable. The Atlantic Ocean will have completely closed and North and South America crashed into each other and into Africa. Southeast Asia will swing around and crash into South America, closing the remnant of the Indian Ocean. This is the next supercontinent, called by some geologists Pangaea Ultima. Iowa will be in a warmer latitude similar to Mexico City today, but will be trapped in the center of the continent, probably on the edge of a great desert. This completes our review of the Cenozoic era and our travels through the geologic history of Iowa, prepared by the Iowa Geological and Water Survey with assistance from the Iowa Limestone Producers Association.